This is going to be a lecture over radiation concepts. It's going to be a review. Hopefully it won't be too strange to you as we go through, particularly if you've seen the summary of physics lecture that this should be uploaded also this week. All right. So one of the things that we need to go through is the physics that encapsulates radiation. Now, up to the end of the 19th century, we really didn't have such a method. I mean, we had Newtonian physics, and yeah, that was enough, right? We didn't have to go any further than that. I mean, it explained everything, right? Well, not quite so much. We started, of course, investigating things like electricity, magnetism, and other things. And then eventually we started taking a look at energy that was released from certain rocks that were just sitting still. And we're kind of like, hey, what's that? And that's where a lot of this got started. So in terms of human knowledge, radiation physics really isn't that old. It's just, it's very important. It covers a lot of things going on here that are going to have a major impact on our lives for both good and bad. And so we need to know how these things work. And that's where we are. So what are the basic things here that we need to know? Well, the basic concepts here is that energy and matter are in fact related. You keep hearing the simple equation put out by Einstein, E is equal to mc squared. Well, that is a relationship between energy and matter. And we use that because it works. It works consistently. It shows us the connection between the two. So energy is defined as the ability to do work. Radiation is energy that is transferred through matter. Matter is a general term that's used to describe the substance that comprises all physical objects. It has shape or form and occupies space. Mass, on the other hand, is a principal characteristic of matter. Matter exists, mass is a characteristic of that matter. It is a quantity of matter that is contained in an object, and we have several different methods to measure that. Grams, kilograms, pounds, ounces, tons, several different ways to do it. I mean, you give humankind enough time and enough ignorance, and they will come up with several different ways in order to be able to measure the same object. So, what's the difference? What's the difference between mass and weight? Weight is going to be defined as the force that an object exerts under the influence of gravity. So, if you're here on Earth, whatever mass that you contain is being accelerated by the Earth at 9.8 meters per second squared, depending on where you are on the surface. It can change a little bit. We take that accepted value of 9.8 simply because it's an average. It's sort of a convenient value that we can use in several different places to give you a really good idea as to what the acceleration is. But it can be different in different places. And also, if you're on different astronomical bodies, you will experience a different acceleration, and that different acceleration will give you a different weight. Your weight on the moon is going to be different from your weight here on Earth. So that has to be taken into consideration. Mass, on the other hand, is just going to be a quantity of matter. That quantity is not going to change no matter your location. You're always going to be, have 10 kilograms of mass no matter where you go. So that's something, that's a distinction that you need to carry with you. So one particular flow chart that we have here is that we can go from matter, and matter can be a mixture. This mixture can be certain substances. The substances are made up of elements or perhaps compounds. Elements, of course, are made up of atoms. Compounds, of course, are made up of molecules. So what about mixtures? What is this of which I speak? A mixture is two or more substances combined together. Air is a combination of nitrogen, hydrogen, oxygen, carbon dioxide, variety of other gases, several of them mixed together. And a little part here, a little part there, that kind of thing. Substance. Material can have a definite and constant composition. It can be simple or it can be complex. Oxygen is one molecule. Carbon dioxide, of course, is a combination, that is a compound. All right, elements and compounds. Simple substances in pure forms, oxygen by itself. An element, of course, exists of only one type of atom. So take sodium, for instance. If you have sodium by itself, that is considered to be an element. You combine sodium with chlorine, and you end up with salt. So that becomes a complex substance. Salt water, of course, if you take NaCl, sodium and chloride, and you throw in a little water, and you've got yourself something that you it's fun to play in, but you really shouldn't drink it. So there's a large number of possible combinations of elements to create one molecule used in compounds. So by the time you start throwing all of these molecules together, and there are several of them, then you end up with several different combinations as to how something can arrange itself. So atoms, again, as I had stated before, smallest part of matter which has a characteristic of an element, contains a nucleus surrounded by electrons, two or more atoms chemically combined, may or may not be of the same element. So you can take two atoms, you can put them together, depending on how well they combine together, you can have something that is chemically far different from what you had before. If you take pure sodium and you throw that into water, you're going to be in for a huge explosion. If you take chlorine by itself, it is a deadly gas. You put the two together and you end up with table salt. And that is something that is of, certainly far more useful than the other two things that I had mentioned. So now when it comes to atoms, what kind of structure do they have? How is it that they're put together? Well, throughout a large part of the early part of the 20th century, we sat down and tried to figure out exactly how an atom is constructed. And lo and behold, we came on with a few certain principles here. And here they are. That a nucleus consists of both protons as well as neutrons. Now, a proton is going to be something that has a weight that is very, very close to a neutron, but it's going to have a charge that is equal and opposite to what you would have with an electron. If you are interested in referring to what is in the nucleus as a group, together protons and neutrons make a class called nucleons. So sometimes you may need that particular description, so bear that in mind. Electrons are the little point charges. They weigh about, I think it's about 2,000 times less than a proton or a neutron. They orbit the nucleus. So these guys are buzzing around out here. We like to think of this as a planetary model in which they associate around here, but that's actually not accurate. nice little model. It's wrong, but hey, all models are wrong, but some models are useful. So protons and neutrons have almost equal mass, somewhere around 1.673 times 10 to the minus 27 kilograms. Another way to look at the mass of nucleons is the atomic mass number. And neutral or stable atoms have an equal number of protons and electrons. You start stripping away or adding the electrons on the outside and things start to become unstable. All right, electrons, they have a little mass, when compared to protons and neutrons, as I indicated before. They have an atomic mass of close to 0. In other words, it's almost negligible. They do orbit the atom within various energy shells, and electrons closer to the nucleus are at a different energy level than electrons far away from the nucleus. If they're further away from the nucleus, it's going to be easier to be able to pick those guys off than it is if they're closer in. And the reason is that they would be closer bound to the nucleus. So throughout the study of chemistry, they've come up with something that is quite useful, quite ingenious, and it's something called a periodic table. And it's a table of elements listed by chemical symbol in order of increasing atomic mass. So chemical properties are going to be determined by the number and the arrangement of electrons in the orbits around the nucleus. So these are going to determine the row or column that they're going to end up in. So if you will notice, hydrogen, lithium, sodium, potassium, these elements right here, they have certain properties, and this is because there is one electron in a particular shell, in the S shell, and they can easily bond with another. You throw in another one there, and that would actually complete the shell. When you do that, you start ending up with elements that are in this column. As you go further along, you have more and more electrons that are in particular shells, and that will give you certain benefits or certain detriments. If you go all the way out here, these are considered to be noble gases. The reason that is the case is because these have a completed shell and are not looking to bond with anything in particular. So if they're out here, they've had certain completions. If you go through here, you can see that this is one row. They have a certain shell that's been completed. This is a certain shell that is working on being completed, so on and so forth. And then when you start to drop down here, you start to see these elements right in here. They also have certain properties. And then you have certain elements up here that are man-made. Some of them are man-made, some of them are just very, very rare. So the rows represent the period in which the number, which is the number of electron shells surrounding the element in the row. The numbers along the top of each represent the group in which the number of electrons in the outer shell of each element. Let's go through, let's pick on one of these elements. We'll pick on, I don't know, carbon. We'll kind of read through the information here and kind of see what it has to say. Individual boxes contain a specific element, the chemical symbol and name. The upper left represents the atomic number, or Z, as it's sometimes denoted. The upper right number represents the atomic mass of the element. All right, let's take a look at barium here. Chemical symbol is, of course, going to be Ba. Atomic number is 56. The atomic mass, 137.34. If you look at the table, barium is in row 6, so it has 6 orbital shells surrounding. Barium is in column 2, so it has 2 electrons in its outer shell. So it's kind of it's in row 6. 1, 2, 3, 4, 5, 6. Go over here. So we've got it's period 6, group 2, right there. Oops. The atomic number, the Z, is going to be the number of protons within the element. Gaining or losing protons will change the element to a different element. So if you could ever efficiently find a way, like the alchemists used to look for, to change 56 protons to 55 or perhaps to 57, if you can find a cost-effective way to do that, you're in good shape. I don't know of anybody that can actually do that, but if you could, that would solve a dream that's been around for a while. The atomic mass, or atomic weight, mass of one atom, protons plus neutrons, and since the electrons weigh so much less than the protons or neutrons, we really don't bother to add those in. So how many neutrons does barium have? Well, if we're looking at the atomic mass here of 137, we subtract out the atomic number, which is 56, then we come up with a difference of 81, so we've got 81 neutrons. So isotope. Elements containing the same atomic number but different atomic masses. So if you look down at the bottom, you can see several different instances of carbon there. But you'll notice that it goes from 10 or from 12.01 to 14.02 to 10. So you're looking at different isotopes. And iso meaning the same, and tope, if you'll remember the P in there, that's going to refer to protons. So a lot of elements have more than one isotope. So the number of neutrons in an isotope is going to be equal to the atomic number subtracted from the atomic mass. And usually at these levels, they're going to be roughly about the same number of protons and neutrons because you need them there in order to be able to separate out the protons from one another. Now, we had mentioned the shells up to this point. And even though we know that it's not really looking like a planetary model, we're going to go ahead and use that because, well, it's convenient. So electron shells are lettered from the inner to the outer. So the inner shell is going to be called K. The inner shell is going to contain a maximum of 2 electrons. It's all a little fit in there. Electrons stay in the orbital shell because of binding energy, gravitational and electrostatic force. The binding energy of each shell is going to be different, as I mentioned. It's going to be harder to pull those out than it would be one of these others. So the maximum number of electrons contained in each shell is going to be listed here. So the max number of electrons per shell is going to be equal to 2n squared. N, of course, going to be the number of the shell location. So for shell number 1, you're going to have 1. Maximum number of electrons there is going to be 2 because 2 times 1 squared is going to end up being 2. And you can see the letter there that is associated with that particular shell. Shell number 2 is going to refer to the L shell. And since that means that n is equal to 2, the maximum number of electrons you would have in there would be 2 times 2 squared, which ends up being 8. If you look at shell number 3, you would be looking at 2 times 3 squared, and that ends up being 18. So on and so forth until finally you get down to the 7th shell of Q. And granted, I have worked a number of problems in my life regarding electron shells. I don't ever remember getting that far down, but theoretically it's possible. And in that particular shell, you can have 98 electrons, and that's a lot. So the maximum number of electrons in any outer shell is going to be 8. The valence is going to be determined by the number of electrons in the outermost shell. So valence determines the chemical reactivity, ability to give up or share an electron. Atoms with 8 electrons in the outer shell are termed chemically stable. These are noble gas kinds of stability here. So I mentioned valence. What do I mean by that? So this describes the combining ability of an element. So +1 valence is an element with only 1 electron in the outer shell. This element is going to be going to give up or share that electron fairly easily. A -1 valence is an element being 1 electron short in an outer shell for chemical stability. So 7 electrons in the outer shell will have a valence of -1. So atomic charge. In their normal state, atoms are electrically neutral. The total number of electrons is going to be equal to the total number of protons. Ionized atoms have a different number of electrons and protons. Obtain a charge according to the imbalance of electrons or protons, either positive or negative. So as I had mentioned before, you've got sodium, you've got chlorine. So sodium having 1 electron in its outer shell, chlorine having 7. 1 atom is going to give up its outer shell electron to another one that has the space for it. So we end up with something like this. So sodium plus chlorine ends up with sodium chloride. Both become electrically imbalanced, but the 2 atoms are bound by an attraction of opposite charges. So in essence, it really does kind of work out to something that's a bit more stable. So covalent bonding, it's the sharing of electrons. So if we look at water, 2 hydrogen atoms, and they're sharing 1 electron each with an oxygen atom. So you've got your hydrogen atoms here, you've got the oxygen atom right here. So they come in, and so the hydrogen atoms are going to share their electron with the oxygen atom, and poof, you've got something that's far more stable. This is a situation called covalent bonding. So here we've got centripetal versus centrifugal force. Centripetal force is going to be directed towards the center. Centrifugal is going to be receding from the center. So if you've got something here, for centripetal, centripetal is going to be pointing into this. And centripetal means seeking. Centrifugal means that our electron here is going to be running away from the nucleus. Centrifugal means fleeing. So there's going to be a balance between centripetal and centrifugal force, which prevents electrons from falling into the nucleus or from spinning off into space. In other words, the forces that want to keep it bound is going to be in competition with forces that want to pull it out. So the electron binding energy is going to be the strength of attachment of the electron to the nucleus. How much does it want to stay there? So the closer the electron is to the nucleus, the stronger the binding energy. In other words, the more energy you're going to have to put into something in order to pull that electron out. The greater the total number of protons and electrons in an element, the stronger the binding energy of any given electron. Binding energy is going to be measured in kiloelectron volts. So the greater the binding energy, the more energy required to remove the electron from the atom, which means it's going to be harder to create an ion. The energy required to remove an electron from a specific shell must be equal to or greater than the binding energy of the electron. Otherwise, you're not going to be able to do it. So here's the example of the binding energy. So all of these are negative because they're wanting, you're going to have to put energy into the system in order to be able to pull these things out. So let's say you've got an atom nucleus here that's got 74 protons, 110 neutrons. And let's say you're wanting to pull one of the electrons out of the K shell. That's how many kiloelectron volts it's going to take in order to be able to do it, 69.5. If you want to pull one of the 8 out of the L shell, you're going to need 12 kiloelectron volts. As you continue to move outward, what do you notice? That energy requirement to pull them out gets smaller and smaller. Now, one of the things that can happen here is that if you've got an outer shell electron fills the space occupied by an ejected inner shell electron, the energy equal to the energy difference between the two shells will be released as a photon. So in other words, if you have something that jumps from, say, the M into the L, because the L, one of the L electrons got kicked out, the electron would fall in the shell, and you would also see a photon of 9 keV be released because that energy is not needed anymore. So, and you can see the other differences there is written in red as you go along. So the total difference in binding energy increases the further the shell is from the nucleus. So what we're going to be looking at here is some characteristic radiation when something is exterior is coming in and approaching into the atom. You're going to have releases here depending on where this falls out from, and it's a little hard, I think, to see in this particular diagram. What's going on? So if you've got something coming in here and you've got 80 kVp coming in, you've got something here that needs 10 kVp to fill this particular spot, then you're going to have releases of energy to fill the difference, and that's what these are describing, depending on which energy level has the vacancy and where the electron comes from in order to be able to replace that. So what different types of ionizing radiation do we have? We have alpha. So we have alpha particles that can be released. We have beta particles. We have gamma rays, and we have X-rays. Also have to concern ourselves with. Alpha particle radiation. They originate from the nuclei of heavy elements because that's where you have the greatest concentration of both protons and neutrons. you've got them there, then that's the type of radiation that you would see commonly. So you've got low penetration through the air, you've got low penetration through tissue. You can see it doesn't go very far at all. Beta particles. They are going to originate in the nuclei of radioactive atoms. These also have low penetration through air and low penetration through tissue, although they do tend to go a little bit further than what you see here. Gamma rays, and as well as X-rays. Gamma rays originate from the nucleus of a radioisotope, and this is the common difference between gamma rays and X-rays. It's not so much the energy as it is the place that they originate from. X-rays are going to originate outside the nucleus in the electron shells. So, electromagnetic spectrum. Radiation within the electromagnetic spectrum have characteristics of waves and particles. Obviously, since they're, we're talking about light here, it's traveling at 186,000 miles per second. So you can see those with high frequency are up in this range. If you go to a smaller and smaller frequency, then you can see that these types of rays are what we're going to be dealing with. So frequency and wavelength. Frequency is going to be a repetitious pattern over time. A lot of times you may see oscillating waves or things of that sort. Basically the same thing over and over after it displaces in a certain pattern from, say, the maximum amplitude or peak to trough, that kind of thing. The unit of frequency is going to be the hertz. It's going to be the number of cycles per second. Wavelength is going to be measuring the distance between those repetitious patterns. So the distance is going to be from one peak of a wave to the next peak, and it's going to be measured in, normally it's going to be fractions of a meter. So what is the relationship between velocity, frequency, and wavelength? So the velocity of electromagnetic energy is going to be constant. It's equal to the speed of light. The speed of light is going to be equal to the frequency times the wavelength. So frequency and wavelength are going to be inversely proportional. So as frequency increases, the wavelength will decrease. And as frequency decreases, then the wavelength will increase. Frequency and energy are directly proportional. So as frequency increases, so does the energy. So what happens to energy as wavelength increases? If the frequency increases and frequency and wavelength are inversely related, as frequency increases, then the wavelength will decrease. If, as we had seen here, as the frequency increases, so does the energy. So if a frequency increase means that the wavelength will decrease. So if the wavelength does the opposite and increases, then your energy should go down. So radiation with low frequency and long wavelength are located at the low energy side of the electromagnetic spectrum, radio, television, that kind of thing. Radiation with a medium frequency and wavelength are located in the middle, the visible light. Radiation with high frequency and short wavelength are located at the high energy side of the spectrum, in other words, X-rays, gamma rays, and cosmic radiation. X-rays and gamma rays are also called photons, quanta. It's basically a bundle of energy. Behaves as a wave or a particle, and it depends. You decide. It travels at the speed of light. Once we know the wavelength, then we can determine the frequency. So, discovery of X-rays. Looks like it happened November 8th, 1895. And you know who? Who did it? A guy by the name of William Röntgen. So what are the properties of 12 of the, what are 12 properties of X-rays? They're highly penetrating, they're invisible, they're electrically neutral and not affected by either electric or magnetic fields. They're produced over a wide variety of energies and wavelengths, release very small amounts of heat when they pass through matter. They do travel in straight lines, travel at the speed of light. They can ionize matter. They can cause fluorescence of certain crystals. Cannot be focused by a lens. They do affect photographic film, which is something that physicists can take advantage of. They produce chemical and biological changes in matter through ionization and excitation. And they also produce secondary and scatter radiation. And scatter is a word that you will come to know in this particular course, as well as other parts of radiation therapy. It was often jokingly said to me that if you don't know the answer to something, you just say scatter and you'll be right 50% of the time. Not exactly sure how that bears out over time, but maybe they're right. Anyway, that is another quick summary here of radiation physics and stuff.